Yes, so a few words about this, how renewable energy is converted to gaseous products. And already mentioned, so some different routes to hydrogen, and also how the hydrogen is produced via this electrolysis route, and some words about the methane or methanation process. And okay, so I have listed here 6 different hydrogen production processes, and this so-called steam methane reforming, it's probably the, like it says here, this most widely used method for producing hydrogen. And it's this very classical chemical or chemical industry process. So it utilizes typically natural gas or methane as a starting material, and of course that normally comes from fossil sources. And then it's treated in roughly very high temperature with very high temperature steam, and also there is the catalyst involved. So typically these industrial processes are using some kind of catalytic materials. Often these catalysts are in these continuous large-scale operations, so these are so-called heterogeneous catalytic materials. That means that they are solid. There is a solid carrier matrix, and it contains the catalytic functionalities. Very often it is some metals, tiny metal nanoparticles that are the active sites promoting the reaction. But there are like hundreds of different catalytic materials. During this course, we will not very much talk about these, but you will find these catalytic materials also in the electrolysis applications. So the cathode and anode surfaces contain catalytic materials, catalytic functionalities. And this catalyst can be found in steam reforming. And like it says here, so basically majority of hydrogen produced still today is made via this steam reforming process. This you have already heard, that number 2, the electrolysis. So it refers to splitting or breaking the water molecules to its starting materials, so hydrogen and oxygen. And that is a non-spontaneous reaction, and it's run with the input of electricity, input of energy. And during the course, so many of the articles that we have so explain in more detail this electrolysis process. And this is the key to the, let's say, this so-called green hydrogen, what we have talked a lot during this course. So we use renewable energy and electrolyze water to make hydrogen. Also, we make oxygen, but like for many of these processes and applications that we cover on this course, so we are more focusing on the application of hydrogen rather than the oxygen part, which of course is the stoichiometric product. So you get 2 hydrogen molecules and 1 oxygen, two hydrogen atoms and 1 oxygen atom. And this 2-to-1 ratio will not change no matter what you do. And then you can do gasifications. So can do coal gasification and end up with the mixture of products here, hydrogen and some side, in this case, side products, CO and CO2. And hydrogen can be then separated from these other products in further processing steps. Biomass gasification became quite popular, like some 20 years ago. It was one of the alternatives to replace fossil fuels. So the biomass can be like some kind of lignocellulosic waste material. So whatever woody material, plant material works okay. And basically after some purification steps, so you can have hydrogen and some other products from these gasification reactions. These are, let's say, not that common, but there are biological processes that produce hydrogen, and I'm personally not very familiar with how these work and what is the, let's say, significance at the moment on these. Also, some of the reference materials mention direct solar water splitting. So these are a few examples, but keep in mind that the large majority volume is in steam reforming, and when we are talking about power to X applications, so what we hope is to boost the electrolysis part, so make the green hydrogen that would basically cut. The idea is that we focus on electrolysis and try to get rid of this, which is current main technology. And what's the hydrogen is the simplest atom and more or less simplest molecule if we exclude the noble gases, which are monoatomic gases. So very simple molecule, and like yet it's extremely important for current oil refining, current chemical industry. And I have listed here some areas where hydrogen is crucial ingredient, raw material or such. And when we talk about petroleum refining, so basically producing all sorts of modern hydrocarbons, fuels, and lubrication oils, and many other basic chemicals. So there hydrogen is used in several different processes. Key ingredient, what we already checked last time, is for Haber-Bosch ammonia production process utilizes hydrogen as the raw material in addition to nitrogen. This is very general chemical manufacturing, so hydrogen is used in various different processes. Then metal processing, so processing and manufacturing utilizes hydrogen. It can be used in electronics production. Of course, if you have a fuel cells in a vehicle or some electricity generation applications, so you need fuel for the fuel cells, and in quite many, like this PEM type fuel cells, also the alkaline fuel cells, so the one fuel is hydrogen gas. Food processing, and I think here it refers to the hydrogenation of vegetable oils and fats. Still, like this margarine is in some cases made through hydrogenation of the unsaturated vegetable oils. So there the liquid oil becomes more or less solid, so it gets this butter-like texture with the help of hydrogenation. But there are other methods that are more popular nowadays, but chemically this is quite nice process. So you apply molecular hydrogen gas, catalyst, and hydrogenate the oils. So basically there are carbon-carbon double bonds that are saturated into carbon-carbon single bonds, and the fats and oils become more solid, or let's say the melting point decreases. Energy storage, of course, is closely linked to the concept of power to X. So one possibility to store renewable energy or renewable electricity is to via electrolysis of water to produce hydrogen. And then, of course, hydrogen is a fuel. It can store energy, so that's one possibility. Here is list of some reactions that was not mentioned in the leftmost column. So methanol production, like also the Fischer-Tropsch reactions, these need hydrogen for the reaction. Then whenever there is some hydro prefix in that process, so it typically refers to utilization of hydrogen. So it doesn't refer use of water, but hydrogen. So hydro this, hydro that, hydrogenation, hydroformylation, hydrocracking, hydrodesulfurization, hydrotreating. So all these processes use hydrogen. I had here, okay, sharing stopped at the same moment. So I have here here just a moment. Uses of hydrogen. This was taken from the link that some of the chapters contain, but the picture is quite okay. So it collects some of the hydrogen-related applications. Also here is the different energy sources that are used in the manufacturing process. And you'll see here some figures regarding hydrogen demand, or how much is being produced. So we are talking about some 80 megatons per year, so quite large amounts. Okay, I have this as its own slide. So this comes from the Global Hydrogen Review from 3 years back, roughly. This we didn't talk very much, but like maybe it's more or less the same hydrogen, whatever the starting material or the energy source is. So like molecular wise or chemically, it doesn't change, but it's anyway, this kind of color coding has been developed to I haven't memorized this ever by heart, so I'm not sure if you talk about pink or yellow hydrogen. I don't know necessarily it's meant by it. But basically, it refers to this like what's the origin of hydrogen? Is it water? And what is the energy that has been used for the electrolysis? So basically, green hydrogen, water plus renewable energy. If it's pink hydrogen, it's water plus nuclear energy. If it's yellow, it's grid-based energy or electricity. And here, these black, gray, and blue are utilizing fossil resource as source for the hydrogen molecule. This slide I showed you last week already, but basically, so if you want to break water molecules, so H2O, so you can do it by putting energy into the system, and it's put in the electrolysis cell in the form of electricity. And there are two in electrochemical cell. There's always two electrodes, the anode and the cathode, and different reactions take place in anode and cathode. And if you combine those reactions, so then you get the so-called overall reaction from that electrochemical cell. And sometimes these acronyms are these HER, OER are used in the articles. So this refer to hydrogen evolution reaction HER and oxygen evolution reaction OER. This I showed you already last time. So it's depending also on the media, that is if the electrolyte or the media where the reaction the aqueous solution, if it's acidic or if it's basic. So on the molecular level, the reaction mechanisms are slightly different, but the overall reaction is the same. So water molecule breaks into oxygen gas and hydrogen gas. But what happens there in the molecular level is slightly different. Then the high temperature it's not happening in any aqueous media, but basically just high temperature, very high temperature, and the water molecule breaks there. So so here are three different electrolysis systems or techniques. The acronyms are like alkaline, so AWE. This is the oldest electrolyzer or technique. Then there is the PEM, so that's refers to the proton exchange membrane. And this AEM is anion exchange membrane. And then there is the high temperature solid oxide, SOWE. So basically these alkaline and proton exchange membrane are quite common. The same applies to the solid oxide electrolyzers. These are, I think, commercially more or less in use, at least what I read. So the anion exchange membrane is still being developed, so it's maybe not yet such developed or established as these other technologies. you want to understand the electrolysis better or in detail, so you really have to study electrochemistry a bit. So that requires some understanding of what happens there. You can calculate many things, but this is not part of the course. But I was mentioning these electrodes, so where the oxygen evolution takes place or the hydrogen evolution takes place. So these, you will see these different metals here, basically. Perovskite is not a metal. Also nickel on YSZ, it's nickel is metal, but this other one is this zeolite type support material. Perovskite, if I remember, it's also some kind of inorganic material. But the others are more or less like contain these different metals. Usually those are in very, very fine, tiny particles, because there you maximize the surface area of this metal. These processes take place on the surface of metal or the catalytic side. So therefore you want to get maximum performance, so you maximize the surface area of these. Nickel is not an expensive metal, but we talk about iridium or platinum, those are extremely expensive materials, so you don't want to waste them. So you want to maximize their surface area and utilization. Okay, what else? Here is some order of magnitude. What's the cost per kilowatt hour? And no, does it make sense? Or here is energy consumption cost. Okay. The time. I think we'll have 15-minute break now. It's more or less 6 o'clock in the Central European time. So I'll continue with the other rest of the slides then after 15 or roughly 15 past. So let's have a short break. So we'll take a look at now this different types of water electrolyzers, not in detail, but some additional info. So on the right-hand side, these all have been more or less copy-pasted or taken from the article number 14, which is the one of the this chapter 4's articles. So here you will see the electrolyzer cell. It's a very, very schematic drawing, so it just illustrates the, let's say, key elements. So here are two electrodes, like in all electrochemical cells. So you have anode and cathode, and different things happen on both of these typically. So the anode reaction is described here. So basically formation of oxygen takes place at the anode, and then on the cathode side you form, or hydrogen gas is evolved or generated. So here on the right hand side, this electrode is the cathode, and the left hand side electrode is the anode. And when you put electricity between, or electrical current between the two electrodes, so then this reaction proceeds. Basically, you end up, if you calculate these reactions side by side together, so the charges typically cancel out, and what you get is water and then hydrogen and oxygen as a result. So these are called side reactions, and the overall reaction is sum of these two reactions together. And in each of these electrolyzers, there is some called diaphragm, or it's some material that is preventing like direct connection between these two electrodes. And also this hydroxyl ion, let's say mobility from the right-hand side, from the anode to the cathode, is happening here. This is the one of the first electrolyzers, so the alkaline, and the environment around here, so it's alkaline, so it's water, hydroxide, so some kind of, well, potassium hydroxide solution. And here nickel and cobalt oxides are found as these catalytic elements on the anode and the cathode. So nickel on anode side and cobalt on the cathode side. So different metals. Why different? So it has been optimized so that the different reactions proceed best, or it's a kind of a compromise. So overall best results can be obtained with these metals or metal oxides. This potassium hydroxide solution is not, or it's quite concentrated if it's 30-40%. And yeah, I guess there is more readable text, better understandable description in this article number 14. So you find it there. There is also more details about this, but I haven't, like I said in the beginning, I will not copy paste all these lecture slides here. Proton exchange membrane. So it's a very typical type of electrolyzer as well. So basically the operating temperatures are mentioned here, so not that high, and catalytic materials are more expensive compared to this alkaline. So nickel and cobalt, if I have understood correctly, so these are fairly inexpensive materials compared to iridium and platinum, which are very expensive materials. But this particular type of setup works or requires these metals, noble metals. The membrane here is very thin, this kind of polymer film, or Nafion is this trade name for it. I think in some materials there is more discussion about the material and how it works and so on, but it's crucial. It's the main thing here, that the electrodes are separated with this membrane that allows only movement of protons from side to side. It prevents movement of the gases and other ingredients in that cell. So the reactions here have been described. So basically how it was here. So let's say hydrogen evolves at cathode side. here is the same. It's not always the same. It depends the type of electrochemical cell or electrolyzer. Solid oxide electrolyzer. This was so the solid oxide, basically this what is between the electrodes. So again, preventing these gases and these from freely mixing with each other. And the mechanisms are slightly different, but the end products are of course the same. So gaseous hydrogen, gaseous oxygen. But the temperatures are much higher in these solid oxide electrolyzers. So we are approaching 1000 degrees Celsius, whereas here it's 100 or less. This was the fourth type of electrolyzer cells, so anion exchange membrane. And here are the reactions, quite similar. And is there something else? This last point here, perhaps, that it still maybe requires some research and development or improvements to be very effective type of electrolyzer. But what is there on the plus side is clearly these non-noble metal catalytic materials can be used, and it may cut the production cost quite a lot. So it very often is that there is some kind of bottleneck with certain things which are at first sight maybe irrelevant, but when we approach commercial applications, so very relevant. And one thing here is that I have been dealing with like 20, 30 years more or less with catalytic materials, and there is always the discussion that how to take most use out of these very expensive catalytic metals. And of course, that is one, the investment cost in the metals, but there is also various things that are of concern, and like what is the lifetime of that catalytic material? Does it require some regeneration and many things? So it's not always directly the cost of metal, but how cheap it is to produce, how durable it is, and so on. You can Google what's the price of iridium, for example, per kilogram. I don't know at the moment, but I would guess that it's expensive than gold. The same applies to the platinum and palladium, which is also a typical catalytic metal. This comes from the very same article, the table. The idea is not for you to read it now during this presentation, but I will refer to that article. So if you want to get more details what the materials, for example, are in these electrolyzer cells, so you find here anode related materials, cathode membrane, also this ionomer, or it's that conductive electrolyte, conductive phase, that like this, there has to be some conduction between the electrodes, otherwise the circuit is not closed and the electrolyzer cell will not work. So the electrical current has to go through the system. Also something about operating conditions and things. This is just maybe to give you an idea that there are some similarities, but quite big differences also in these type of materials. So when it comes to the catalyst and so on. But this is just for your information to have an idea about the different types of electrolyzers. And the setup and things are explained in the article better. This I remember showed you last time. So basically it's what when we talk about this anode and cathode and the membrane and so on, so then we are in this very center in that electrolyzer cell, but in order for it to become somehow working unit, so there are like upstream and downstream units prior to this electrolyzer cell that are essential for the operation. And typically it's something like here separation or purification or that type of steps that are needed for the operation. Here also is compression because it's a gaseous material. This is a bit more detailed scheme, but basically the tells the same things, but maybe there are a few more details. But the electrolyzer, like where the chemistry happens, so it's here in the very center, and then here are separation units and also some other things. But it's not only about the electrochemical cell or electrolyzer cell, but there are various other elements that are needed. So that was in short, very short, the water electrolysis. So this is quite hot topic in the research literature. So if you search with hydrogen water electrolysis, so you find thousands of articles. So the main problem with this is that there is so much information and material that makes it difficult. Not that there would not be information at all, but there is too much, at least for quickly to get an idea what this all is about. So then, if we come to the second topic, so production of methane. So as you know, methane, CH4, so it's the simplest hydrocarbon. Hydrocarbons have carbon and hydrogen, and depending on the structure, so this ratio can vary. But this is the simplest hydrocarbon, and of course it's used as a fuel, so you can burn it for energy, can use it for as a fuel, produce heat, and then its industry refers to, for example, it can be used as a starting material in other chemical reactions as well, like for making of hydrogen. So hydrogen is made from methane, or can be made from methane. Like in that steam reforming that we talked in the very beginning. But basically this is the so-called, what I mentioned, secondary conversion. So in this, at least this slides, what I'm showing here. So what you have is the green hydrogen, or this is the ideal situation. So you take green hydrogen. Of course, all hydrogen is the same molecule on a molecular level. So it would not change this process, but of course it would kind of ruin the idea of utilizing renewable energy source and cutting the fossil raw material use. Then the other ingredient is carbon dioxide, and we haven't covered during this course very much, but some of the articles describe the typical methods and sources for CO2. But carbon dioxide and hydrogen then processed with, this is classical catalytic conversion, so high temperature catalytic materials and ingredients, and then you end up with methane and water as product. Regarding the carbon dioxide source and concentrations. So I just copied this from the article, but basically it varies a lot. So if you capture it from the air like this duck, so you have very, very low amounts of carbon dioxide available. Usually if you try to extract things from very diluted mixture, so it tends to be more difficult, more expensive. But if you can use the different sources, like let's say biogas upgrading or bioethanol production, in regular bioethanol production or ethanol fermentation, so you end up with liquid ethanol, and then you end up with gaseous carbon dioxide. So the more or less most of the gases exiting the fermentation vessel are pure carbon dioxide. So for example, that is probably fairly cheap to utilize compared to the direct air capture. And here are other examples of processes or industries that emit or produce carbon dioxide. So in this sense, it's the carbon dioxide produced. It would be collected and utilized as raw material for making methane again, or converting it to methane. This process or reaction is called Sabatier process. It's a very old invention. Like I showed you, many of the classical chemical industry processes and reactions are more or less 100 years old. I think the same applies to this. So here you see the reaction scheme. Carbon dioxide and hydrogen combine. You get the desired methane, and in this case, a side product, water molecule. So it's a mixture of methane and water, but of course, these are very easy to separate from each other. Water is, if you lower the temperature, water condenses to liquid and methane remains as a gas, so this is not a very challenging separation. The reaction conditions are quite harsh, so 300-400 degrees Celsius and quite high pressure, so 3 megapascals. And again, we end up with these certain catalytic materials. So here metallic nickel or ruthenium on alumina. Alumina is the catalyst support, and the nickel and ruthenium are deposited on the alumina. And all these reactions happen on the surface of the nickel metal or on that surface of ruthenium. Certain grades of alumina have also acid functionalities, but I'm not sure if this Sabatier process catalyst have some acidic alumina. But in the course materials, there is an article, I think, that deals with this process, so you can check what other details this have been published about this reaction. So here is the bigger picture. So basically, if we want to do this Sabatier process, and if we are in the context of power to X, so this is that classical secondary conversions that we get these problematic raw materials, carbon dioxide from the air or some other sources, and hydrogen from the electrolysis of water. The hydrogen electrolysis, it's not a problem, and neither is the CO2 in that sense, but if we think that in the future we want to collect all the carbon dioxide from different processes, so that becomes a problem, because you have to store it somewhere, and you cannot easily store all the CO2 emitted in the world somewhere. So this is like one example that there is a way to convert the collected captured CO2 into somewhat useful products. So basically then it's quite typical then that this comes backwards. So when we burn the methane, So we end up with carbon dioxide, and then it's kind of a cycle. So we put energy in this electrolysis step into the system, and then we extract the energy when we combust the methane. So it's going in this kind of cycles. Here it's collected in like more complete scheme. So this should be already known to you. So we use renewable energy, solar, photovoltaics, wind energy. Then we electrolyze the water. Here you get the hydrogen for the methanation reaction. We capture carbon from various sources, which is available, which is the cheapest or makes more sense, and mix these hydrogen and carbon in that reactor, apply the catalyst and high temperature. That converts to methane and water. And of course, here is some purification or separation step before this methane can be used for different applications. Also, here is like in all this water electrolysis, so there is side product, or one product is the oxygen as well, but we haven't discussed where it could be used, but certainly oxygen is also used here and there. And this was in short about the power to gas, like section 4 contents, but just two examples. So basically how to convert the power to gas concept. So hydrogen is of types of its own, and then the secondary process of making methane. But there are other examples, and if you go through literature, so like I said, so it's more of a challenge to see that there are so much information, so many catalysts, so many reactions have been studied already, so that take these as kind of an examples of power to gas concept.